What we're going to be looking for in this activity here is that we want to see how this numerical constant b affects the graph. And we want to see what happens when we put it into this form y equals m times x plus b, where this is our multiplier and this will represent the slope of the graph. Okay. And b then represents a numerical constant. So we want to see how that numerical constant fits in. So when we look at the b value, so when we look at the m value, all these have an m value of 2. And when we graph these coordinates, we can make a table of values and graph these. I can see that this graph has this slope of 2, this graph has a slope of 2, and this graph has a slope of 2. These are all parallel lines, but they all have slightly different positioning. So how does that positioning work? Well, when I look at the positioning of this, this 0 seems to indicate that when x is 0, y is 0, so it indicates this point right here, or where it crosses the y-axis. This -3, again, is when x is 0, y ends up being -3, so it represents this point right here on the y-axis. And when we have 2x plus 2, when we plug in x is 0, y equals 2, so it represents this point here on the y-axis. So when we look at that numerical constant, really it's going to be the value that's left over when we plug x is 0 into our equations, and it represents our y-intercept. And when we write it in our equations then in this y equals mx plus b form, well, the m indicates the angle or slope of the line, and the other characteristic that we want is positioning. And that b represents a very useful and convenient positioning. It's positioned at 0 on the y-axis. Here, this -3 means it's positioned at -3 on the y-axis. This +2, when we write it in this form, it indicates the position of 2, the initial position of +2 on the y-axis. So these three lines, they all have the same slope. In this case, it was the m value. And they are not the same lines because they have different vertical positioning. I suppose technically we can say that they have different horizontal positioning as well, but we're going to look at this from a vertical perspective. So when we look at these graphs, then if I take a look at 2x plus 6, well, they should share the same slope as 2x plus 0. The difference is the vertical positioning will be different because of that plus 6. And I want you to check these by graphing, put them in Desmos and actually graph them, and you should see that these two lines both have a slope of 2, so they should have the same angle as these lines, but they have a different vertical positioning. And in fact, we can see that these lines, we should expect this line to cross the y-axis at +6. We should expect this line here to cross the y-axis at -5. Okay? So what we can then say is that what's the conclusion we can make about this? And I want you to highlight this. What is the main idea then? How does the numerical constant of the graphing equation change the graph on the line? Well, that numerical constant is going to tell us where the graph crosses the y-axis. So the numerical constant b this is b in the y equals mx plus b equation, tells us where the graph crosses the y-axis. Okay. We also can find this coordinate by saying when x equals 0, okay, we end up with equation that looks like this. Y equals mx, and when x is 0, plus b, well, the b value, okay, we can see that then the y value is going to be equal to b. So we end up with y equals the b value, which is in what we call the y-intercept.